طيب, Bismillah ar-Rahman ar-Rahim. We started talking last time about analog transmission, where the transmitted signal over the transmission medium. So if we have a transmission medium of that has bandpass effect, then we need to, at the transmitter side, we need to modulate, or we need to do some conversion from a digital signal to analog signal, okay, so that we can shift the frequency properties of this signal in the frequency domain, hence align with the bandpass effect of the transmission medium. So we talked about ASK, where the analog signal, okay, changes its amplitude according to the bits from the digital signal. So if we have a bit of 1, then we send a sine wave, okay, with a fixed frequency and certain amplitude. And when we have a bit of 0, then we send a sine wave with amplitude 0. In other words, we change the amplitude of the analog signal according to the digital bits that we have. Then we talked about the fact that this ASK, or the analog shift keying, has a certain problem that has to do with the noise resistance. So in which case, as we discussed last time, if we were to use the frequency, to change the frequency according to the digital bits, then we would be more noise resistant. So so we talked about FSK, we talked about the minimum phase shift keying, frequency shift keying, or binary frequency shift keying, where we changed the frequency of the analog signal according to the bits, whether it's 1 or 0. So 0 would be low frequency sine wave, and 1 would be a high frequency sine wave. And we said that for implementation, we use the hardware circuit of the voltage controlled oscillator, because this circuit tends to have a coherent FSK, where we avoid the discontinuation here. So this is continuous signal. Okay, so we avoid the discontinuation in the signal, which really degrades the performance in terms of frequency, because if we have discontinuation in the signal, this will result into a very high frequency components, which will degrade the performance for FSK. So today we need to talk about the general case of FSK. So if we have more than just binary FSK, so unlike the case of ASK, if we try to transfer 2 bits at a time and convert it into a symbol, then we will have a sine wave with different amplitude, right? In which case, in terms of bandwidth, it would be more efficient, because we are sending multiple symbols that have different amplitudes to represent more bits, more than 1 bit. So it would be 2 bits or 3 bits. So if you have, like for example, if you have to represent 3 bits, then we need 8 different levels, voltage levels, for the sine wave when it comes to ASK. So, however, for the case of FSK, unfortunately, we have to change the frequency for the different symbols. So each symbol will have to use a different frequency range altogether. So if we need to represent 3 bits, which is what this exercise talks about, so if we need to send data 3 bits at a time, so in which case, what's R, ya shabab? So each 3 bits would be represented as R is the number of digital elements over the number of signal elements. So it's 3 over 1, so it's 3. The signal rate is actually n multiplied by 1 over r, right? So supposedly when I represent more bits as a symbol, supposedly the signal rate, okay, will be more efficient, صح? And that's the case for ASK. However, for FSK, we have to change the frequency for each symbol, unfortunately. So if we have, if the bit rate that we want to send is actually 3 megabits per second, so in that case, so what's S in that case? So S equals to 3 megabits per second times 1 over R, which is 3 times 1 over 3, which is 1. 1 إيه 1, what is the unit here? No, signal rate has the unit of baud. So this is 1 mega baud. Okay, so pay attention, pay attention to the units. Okay, so in the exam I can give you multiple steps. So if you write the units incorrectly, then you lose points for no reason. Okay. Baud, no, it's baud. Baud is actually, يعني, baud is the unit for the signal rate, and the signal rate is the amount of change per second. Yes, it's the amount of change per second. But in terms of units, the signal rate is measured using the baud, and this is actually 1. This is not 1000 here. Type. So this is this is S. So what is the bandwidth for one symbol? Okay, the bandwidth for one symbol, as we said last time, is 1 plus D times S, where D, as I said before, is the filtering factor, and it ranges from 0 to 1. Okay, it ranges from 0 to 1. So assuming that D here is 0, so if D is 0, then the bandwidth for one symbol is 1 plus D times S, which is S. And for the case of FSK, we have to add here 2 delta F, right? This is for the case of binary phase shift keying, okay? However, if we need to represent 3 bits at a time, then we have in total how many symbols? How many symbols do we have in total? How many different symbols do we have in total? 8, yes. So what would be the bandwidth then? So if we have, so let's just draw the frequency domain of this. So here in the example here, we say that the carrier frequency is 10 megahertz. See that? So the carrier frequency is 10 megahertz, and of course the number of levels is 8, because we need to represent 3 bits at a time. So we have 8 different levels, or of course for FSK, the level for us is not a level of voltage. It's actually a different frequency, right? So we have 8 different frequencies, all of them around the 10 megahertz carrier frequency. Okay, so now we have 8 different symbols, okay, around the 10 megahertz frequency, right? So each of these frequency ranges represent a separate symbol, and we said that actually the 2 delta F is here, okay, and the more 2 delta F we have, the more guard bands we have between the symbols, in which case we may have some separation between the different symbols. Here, if we calculate 2 delta F is actually 1 megahertz, And if we calculate the S is 1 megabaud, which means that the bandwidth for one symbol is also 1 megahertz. So the 2 delta F is 1 megahertz, which is the minimum separation between the two symbols, right? So so each of these symbols is actually 1 megahertz. Okay, so in total the bandwidth is the bandwidth in total is for all the 8 symbols. The bandwidth is 8,000 megahertz, right? It's so 8 megahertz, yeah, Daniel. 8 megahertz. So we have 1 megahertz per symbol, which means that we have 8 megahertz, 8 megahertz bandwidth in total, right? Right. So if we have this 8 megahertz, then we can transfer the FSK 3 bits at a time for all the 8 symbols. So the bandwidth in general. So we want to write the general formula for calculating the FSK bandwidth in general. So in other words, the bandwidth for FSK as a function of the number of different levels equals to the bandwidth for one symbol, which is 1 plus d times s, plus 2 delta f, right? Which is the separation between the different symbols. What is the number here? What is that scale? What is this weight? L. Okay, so if it's L, this means that for this particular example, L is 8, okay, and we have 1 plus d times s here, right? So 8 and 1 plus d times s becomes 9. So this is in fact L minus 1. Why? Because L minus, why? I'll tell you why. Because we have this part, we have this part here, and we have this part here, okay? If we add those two red ranges, okay, together, they become the bandwidth for one symbol, which is 1 plus d times s, right? And between each two symbols, here we have 2 delta f, 2 delta f, 2 delta, and so on, right? So so you have in total L minus 1 times 2 delta f, okay, plus the two halves, the two red halves at at either side, at both sides, right? So 1 plus d times s plus L minus 1 times 2 delta f. So this is for any arbitrary 2 delta f. So if I tell you that I can ignore, or I can give you no value for delta f, for 2 delta f, and I tell you calculate the minimum bandwidth. The minimum bandwidth is when 2 delta f equals to لا لا يا لا 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 I will mute you Daniel عشان I don't want it to be يعني a one man show. So if what is the minimum bandwidth? What is the value of 2 delta f for calculating the minimum bandwidth? Remember, 2 delta f is not the guard band. 2 delta f is the separation between the two middle frequencies of two consecutive symbols. Okay, so it's actually the distance between this middle frequency and this middle frequency. So it's this, not this. So when the guard band is 0, what is the value of 2 delta f? the value of, for this particular example, it's 1 megahertz. صح. In general, it is 1 plus d times s. In general, it's 1 plus d times s. So when the minimum value for 2 delta f is 1 plus d times s. Okay, which means that the minimum value for the bandwidth is actually 1 plus d times s times l. This is the minimum. Okay, I can give you a problem like this, and I tell you, instead of telling you calculate the minimum bandwidth, I'll tell you calculate the maximum bit rate for this, and I give you the bandwidth. Same thing. The maximum bit rate is when 2 delta f is a minimum. The maximum bit rate is when the 2 delta f is minimum. What is the bit rate? The bit rate is here, s. S is actually n times 1 over r, صح? So n here is the bit rate. Okay, so just pay attention to the different combinations of this. Okay, so in other words, if I want to send more bit rates for ASK, the problem was easy. Okay, so just increase R, which means increase the number of bits that you can represent using one symbol. And in that case, you will send more bit rate in a small bandwidth. In FSK بقى, we did not succeed to do this, because if you increase the value of R, this means you increase the value of L, right? So, and the bandwidth is actually inversely proportional to R, but directly proportional to L. In other words, we cannot fool FSK when it comes to sending more bits in one symbol, right? For ASK, we were able to be more bandwidth efficient, okay, by increasing the value of R. But here, we cannot do that, because if we increase the value of L, this means that we transfer more symbols, and more symbols means more frequency, and the bandwidth becomes bigger and bigger and bigger. واضح? What is the advantage for FSK? Well, the advantage is more noise resistant. So we are becoming more noise resistant, which is good, because ASK, by increasing the number of levels, we will be more prone to noise, and we will study this very clearly in the next few slides. طيب. So this is how the spectrum looks like for this example. Okay, so you have the carrier frequency here around the 10 megahertz, and you can easily calculate the middle frequencies for each symbol. And as I said, we selected here 2 delta f to be 1 megahertz, which happens to be the minimum 2 delta f, because 1 plus d times s is also 1 megahertz. So 2 delta f here. So as we said, the motivation behind FSK is to be more noise resistant, is to try to reduce the effect of noise. The cost here is that we have increased the bandwidth exponentially. So we increased the bandwidth quite a bit. So the question is now, can we have the same feature of noise resistance, but without increasing the bandwidth? So binary phase shift keying tries to answer this. So instead of using the amplitude to represent the bits or the frequency to represent the bits, we will use the phase of the sine wave. So for example, the binary phase shift keying, we use the sine wave with phase shift 0 to represent the 1, and with phase shift 180 degrees, okay, or pi to represent the 0. So here we use the same amplitude, same frequency, but different phase. So because of the fact that we did not change the frequency, the bandwidth here, the bandwidth stays the same, like ASK, okay? So the bandwidth here is 1 plus d times s. And there is, by increasing the number of symbols, we do not increase the number of frequency ranges like FSK. So here it's one frequency range, 1 plus d times s. So as we have learned in life, nothing comes for free. Okay, that's a general rule. So remember, phase is like frequency when it comes to noise resistance. Phase is also noise resistance. So noise tends to have less effect on the phase compared to the amplitude. So phase shift keying tends to have the same advantage like the frequency shift keying when it comes to noise resistance type. What is the cost here? Remember, we talked about the effect of non-coherent FSK, where we said that if you have a discontinuation in the signal here, okay, this tends to have high frequency components, right? So in FSK, we were able to avoid this discontinuation by using the phase, the voltage controlled oscillator, which allows us to generate a coherent FSK, and this is continuous, right? In PSK, we cannot do that. The discontinuation here is by design. We have to have that. We cannot avoid this because changing this discontinuation means that you have to change the phase, and we cannot do this. واضح يا شباب? So we cannot get rid of the discontinuation. And that's why there are two costs or two disadvantages that we had to pay for the phase shift key. One, the value of D, because of the high frequency components due to the discontinuation in the signal, the value of D tends to be close to 1. Remember, we said that in general, the value of D is from 0 to 1. The value of D here tends to be close to 1. Okay. Number two, the receiver design is very complex. Why? Because here the receiver needs to detect not the amplitude, not the frequency, it needs to detect the phase. Detecting the phase at the receiver requires a very specialized circuit. It's called phase locked loop. This phase locked loop tends to be very complicated at the receiver side. Okay, so the receiver design is complex, and the value of D tends to be close to 1 due to the fact that we have discontinuation. So these two tends to represent the cost that you have to pay for PSK in order to have the very nice advantages that we are bandwidth efficient and noise resistant at the same time. Bandwidth efficient and noise resistant. So we will show you visually بقى in few minutes why the binary phase shift key is very much noise resistant compared to ASK. That's what we need to visualize. So first, for the implementation, it's actually very easy. It's very similar to ASK. Okay. The only difference is that instead of using non-return to zero, okay, unipolar at the receiver side, we will use the non-return to zero polar. Sorry, not at the receiver side, I said at the sender side, because we're not sending this digital signal as is on the line. Remember that this is all at the sender side. So at the sender side, we will use the polar representation of the bits. So it's 1 becomes 1 and the 0 becomes -1, right? And then we multiply that by the carrier. So for 1 the sign becomes sign, for 0 the sign becomes minus sign. Okay, so you end up with a signal that looks like this. This is very easy, right? So so it's very similar. In ASK, remember, the only difference was the input signal represents the 0 as 0. That's it. صح? So that's the only difference for ASK for on-off keying, right? For on-off keying, the input signal was to represent the 0 as 0 voltage, to represent sine wave with a frequency of 0 or with the amplitude of 0. Okay. طيب, if we were to have QPSK, in which case we need to represent each 2 bits as one symbol. Okay, so for the phase, we need to have now sine wave with 4 different phases, right? Because L is 4, right? So we need to have sine wave with 4 different phases. So this is the implementation for what we call quadrature phase shift keying. Quadrature here refers to 4, which means 4 levels. So quadrature phase shift keying represents each 2 bits as one symbol. Okay, so how can we implement this in practice? We will implement this using 2 binary phase shift keying. So what we do is that we have here, this is binary phase shift keying, and this is a binary phase shift keying. And all we need to do is just to introduce, for one frequency, we introduce a phase shift of 90 degrees of pi over 2. If we do this, then we have 2 binary FSK. One of them is shifted 90 degrees from the other. So if we add those together, we get all the 4 combinations that we need. Why? Because as we said before, for each binary phase shift keying, we will have sine and minus sine. And the other phase shift keying will be cosine and minus cosine. Okay? So if we add the sine to the cosine, so it becomes a sine wave with a phase shift of 45 degrees. So in other words, if we look at the composite signal here, we will see a sine wave for with a phase shift of 45 degrees to represent, for example, the 1-1. A sine wave with a phase shift of 135 degrees to represent 0-1, and so on. So all we need to do is just to divide the input bits into a 1 bit at a time, and each bit will be an input for a binary phase shift keying, and the 2 binary phase shift keying are shifted compared to each other by 90 degrees. Okay, so the composite signal here gives you all the 4 phases that you want. Of course, we have used, if you remember, for FSK, we tried to use a similar implementation. However, for FSK, this implementation tends to be non-coherent. Okay, we said that the problem with this implementation is that it's non-coherent FSK, so it tends to have discontinuation. For PSK, discontinuation is by design. It has to be there, so it needs to be there. That's what we are trying to detect at the receiver side, is the different phase. Okay, any questions ya shabab so far? So this is quadrature phase shift keying. If you want to do it this way, then you have to do 45 degree phase shift here, and one minus 40 and one minus 45 degrees here. That's the main difference, yani. So you have slight change in the implementation to have the 4 symbols arranged in the way that you are describing here. So a very quick example. So if we have the find the bandwidth for a signal transmitting at 10 megabits per second. So this is n. So n is 12 megabits per second for QPSK with d equal to 0. طبعا, of course, the bandwidth is very easy. So it's 1 plus d, and d here is 0, times s, and s is n times 1 over r. So because it's QPSK, what's R? Yes. الشام ايه الصعوبة في كده؟ الناس واضح ان هي you are not following. يعني I see that people are not focusing so much. يعني please try to focus. This question is supposed to be very easy. Actually, the answer is here. You just need to follow through the explanation. So R here is 2. So so the S is n times 1 over R. So S equals to 12 times 1 over 2. So it becomes 6. 6 ايه بقى؟ عزام 6 ايه؟ What is the unit here? عزام انا بقول عزام. عزام. خلينا نكتب الاسم. اوكي. عزام. اسعد خليل 6 ايه بقى؟ 6 ميجا ايه؟ لا. Signal rate has a unit of ايه بقى؟ baud, not hertz. Pay attention to this. Signal rate has a unit of baud. Okay. So the bandwidth is equals to S because D is 0, right? So the minimum bandwidth is when D is equals to 0, and the maximum bandwidth is when D equal to 1, which means that it's double B signal rate. The طيب, as we said, we have been طبعا teaching you how to represent the signal in the time domain, and in the time domain we have been able to see some properties of the especially the analog signals, the sine wave with cycle and so on. And we have said that there is another representation for the signal, which is the frequency representation or the frequency spectrum. And the frequency spectrum tends to give us a more visual information about different properties of the signal, which we cannot otherwise see in the time domain. So in the frequency spectrum, we can see the bandwidth of the signal very clearly. We can see how the different frequency components are structured in the frequency spectrum and so on. So that helped us to understand more properties of the signal which we cannot otherwise understand in the time domain. So now we will study a third representation of the signals. This representation is called Constellation Diagram. Constellation Diagram. This Constellation Diagram tends to represent two things: the amplitude of the sine wave and the phase of the sine wave, not the frequency. So the Constellation Diagram gives us some properties related to the amplitude particularly and the phase. So the Constellation Diagram represents the signal as follows. So here we have a dot. So each sine wave, okay, is represented in the all the 4 quarters of the of this diagram, okay, as a dot. The distance between this dot and the origin, okay, is in fact the maximum amplitude of the sine wave. And the angle of this vector of this point from the x-axis represents the phase of the sine wave. So let's take an example. So if we have a sine wave, okay, that looks like this. So here we have a sine wave that looks like this, right? So this sine wave has a maximum amplitude of A, okay? And a phase shift here, the phase shift here, let's say is pi over 6 مثلا, okay? So this sine wave will be represented in the constellation diagram. Sometimes we call it the IQ diagram. So this will be represented, this is the I, Q. This will be represented by a dot. This dot is distant from the origin by a value of A. So the distance between this dot and the origin is A, and the angle here, okay, is pi over 6. واضح كده؟ So that's the how we represent the sine wave with a different phase and different amplitudes. طيب, what is the idea behind the IQ diagram? We'll see in the next slide that this IQ diagram will help us a lot to understand other properties in all the modulation schemes that we talked about, the digital modulation schemes that we talked about, ASK, FSK, and PSK, and بالتحديد طبعا ASK and PSK, not FSK. So we'll understand other properties that we couldn't understand in the time domain, or slightly, okay? But this is يعني slightly easier because one PSK, one binary phase shift keying will have no phase change, and the other one is shifted by 90 degrees. So that tends to be a little bit easier. However, let's talk about how we represent. Go ahead, Daniel. Do you have a question? I stands for in phase. In phase معناها ان the components that have phase shift of 0. So any sine wave with a phase shift of 0 will be represented on the in phase, which means that in the x-axis we represent sine wave with a phase shift of 0 with different amplitudes. Okay, and Q stands for quadrature, which means quadrature phase, which means that any component that has or belong to the pi over 2 phase. So we can have any combination between the I and the Q, as we will see. So this will make this visually clear. So for on-off keying, as we said before, on-off keying tends to represent the 0 as 0 voltage, okay, or a sine wave with 0 amplitude, okay, which means it coincides with the origin, okay, and it has an amplitude of 0 and phase shift of 0, صح? And we used to represent the one as a sine wave with phase shift 0 برضو, but the amplitude changed because on-off keying tends to change the amplitude, not the phase. So it doesn't play with the phase at all, صح? So, which means that ASK tends to have dots in the x-axis of the IQ diagram, always. Okay, so all the ASK tends to have dots in the x-axis, which means that we have a sine wave with different amplitude, but all of them, they have the phase shift of 0. So all of them are represented in the I-axis or the x-axis. واضح? Okay. طيب, for binary phase shift keying, we said that we will represent the 1 as a sine wave with frequency 0 and amplitude A, okay, and the 0 with a minus sign, which means that you have 180 degrees phase shift, and also with an amplitude of A. صح كده؟ So for quadrature phase shift keying, we have 4 different phases, as we have discussed before. So we have this is 45 degrees to represent the 2 bits, 1, 1. We have 135 degrees to represent 0, 1. And you have minus 45 degrees to represent the 1, 0. And minus 135 degrees to represent the 0, 0. Right? So this is minus 135. Okay? So here, we can represent the quadrature phase shift keying as 4 dots in the IQ diagram. Very easy, right? واضح so far? So let me clean this. So now we understand how to represent each of these digital modulation schemes. So ASK, PSK, and QPSK. So again, what is the motivation behind the IQ diagram? So if we try to send these symbols over, so we have this is sorry, so this is the sender now. The sender generates these symbols and tries to transfer these symbols over the medium. Okay, so at the receiver side, the receiver will receive the signal plus noise, right? So the noise that affected the signal through the transmission over the medium. What is the result here? The result that the signal will affect the symbols as follows. So each of the symbols that represent the one, they will be received at the receiver side like this. So it will be, so here it will be like this, right? So these different dots, they represent what each symbol has been affected by the noise when it got transferred over the transmission medium. And the more the noise is, the wider this cluster of points will be. So here we will have برضو dots like this. So again, these dots are showing the effect of the noise on the transmission medium. Okay, so if we see the transmitted signal from the sender, we will see an ideal signal that have dots, predefined dots, exactly, okay, at the origin or at the predefined locations. However, when we look at the receiver side and we try to display the IQ diagram using the spectrum analyzer, we will see that the ideal symbols have been affected by noise and they have been received in the form of clusters like this. واضح يا شباب؟ طيب. So again, so what is the point that we are trying to make here? The point is as follows. So if the distance between these clusters is actually short, okay, you will have more probability of errors because these clusters, they will overlap. They will start to overlap. Okay, and that's why we've been telling you that for ASK, because of the fact that we use only the amplitude and we only use 1 degree of freedom, which is the x-axis, these clusters, they tend to have short distance between each other. So these clusters may easily overlap, in which case you will receive a signal and you will interpret the 1 as 0 or the 0 as 1. So the probability of error increases, right? So as we can see, for binary phase shift keying, the distance between the two clusters is much wider, right? Why? Because now we can use the phase and we can use the negative phase, okay, to represent the 0. And in order to appreciate this even more, we can see that for quadrature phase shift keying, we can actually organize the symbols in the 4 quarters of the IQ diagram, in which case you try to maximize the distance between each 2 symbols, and in that case you reduce the probability of error at the receiver side because you have less probability that these clusters can overlap. واضح يا شباب النقطة دي؟ So this is to show you visually how if we use PSK, right, that we can be more noise resistant. Why? Because for PSK we can use the phase to arrange the symbols very neatly in the 4 quarters of the IQ diagram, in which case we can maximize the distance between each 2 symbols and hence reduce the probability of error. واضحه النقطه دي؟ Go ahead, Danny. Yes, yes, exactly the same. Exactly the same. Yes, exactly the same. All we need to do is just to rotate this. Just what you are saying effectively is to rotate this here and this here and this here and this here. So it's exactly the same. There's no effect whatsoever. Uh, Well, in the implementation, you have to change. Is perfectly correct. So we can have 0, 90 degrees, and 180 degrees, and 270 degrees. That's perfectly fine, and it's perfectly the same. محمد تفضل. This is yes. What is still used? Yes, it is. Yes, of course. Yes, yes. We are using this, and but remember, this is analog communication. معناها ايه؟ The transmitted signal over the medium is analog, but here the input signal is a digital bits. Remember this. Okay, so analog communication here refers to the analog signal that gets transmitted over the medium, right? But the input signal, because because we will talk about the second part now, where the input signal is actually analog. We'll talk about it in a minute. Okay, we'll talk about it next. All right, so now I hope يعني you appreciate more visually how PSK is more noise resistant, okay? Because of the fact that we can arrange the symbols more يعني nicely in the four quarters of the IQ diagram. Hence, we maximize the distances between each two symbols. Hence, reduce the effect of noise. So the idea is why to stop at PSK where we have the same amplitude, right, and different phases. Okay, can we have a mixed digital modulation scheme where we can change both the phase and the amplitude? And the answer is yes. Nothing can stop us. So we have what we call QAM, or quadrature amplitude modulation. So here, quadrature here refers to the phase, and the amplitude refers to amplitude, of course. So this combines the amplitude with the phase. Okay. So in other words, the symbols may actually have a different phase and or different amplitudes, right? So if we talk about 4QAM, then we talk about four symbols, four different symbols. So we can arrange the four symbols like this, right? Or we can arrange them like this. Okay. So which one is better and why? A is better or B is better and why? تفضل يا محمد. محمد علي. B, why? برافو عليك. Yes, so that's exactly right. So محمد علي ايه؟ بحلي. Okay. Okay, so that's exactly right. So here we have for B, we have the distance between each two symbols is much bigger compared to this. Okay, so in that case, the effect of noise here, okay, will be less because the distances are more. Yes, yes, Daniel. No, it's QAM. Here we're talking about QAM. We are changing the in general. Here, by the way, you can call this for QAM. It happens to coincide with the quadrature phase shift keying, because if you arrange those 4 points, you will see that these 4 points they have fixed distance to the origin, which means that you are not changing the amplitude. Until now, we are not changing the amplitude, right? So we are changing only the phase. So 4 QAM is exactly equivalent to quadrature phase shift keying, right? Here, 4 QAM is not equal to or is not identical to the quadrature phase shift keying. Why? Because here we are changing both the amplitude and the phase. The symbols, they have different amplitude and different phase, right? But for B, we are changing the phase but not the amplitude. So the 4 QAM and the quadrature phase shift keying, they are the same, right? Here, for example, this is a very bad design for 4 QAM, right? Very bad design. Yani you have the whole all the 4 quarters of the IQ diagram available for you, and you arrange the symbols, okay, very close to each other in one quarter of the diagram. Of course, here we have different amplitudes, okay, for each symbol, okay, and different phase. And the symbols are very close to each other, so the effective noise here will be very, very high, right? But the main advantage of QAM, okay, modulation, is where you have 16 symbols. So definitely, if you have more than 4 symbols, if you have 8 symbols or 16 symbols and so on, then you can arrange nicely the symbols in the IQ diagram like so, right? And of course, if you have 16 PSK, right, then you have to arrange all the 16 symbols very close to each other in one circle, right? Because PSK, the symbols, they have to have the same amplitude. واضحة دي يا شباب؟ For PSK symbols, they must have the same amplitude. Okay, which means that in the IQ diagram, they need to be arranged in a circle, because the circle will have the same amplitude distance to the origin, right? So you have to have all the symbols arranged in a circle. And as you can imagine, arranging multiple symbols in one circle, right, it will not give you enough degrees of freedom, in which case the symbols will be close to each other, and in that case the effective noise will be more. However, for 16 QAM, we have more degrees of freedom. We have the amplitude and the phase, in which case we can arrange the symbols, okay, using different amplitudes and different phase, in which case we can control the distances between each 2 symbols and reduce the effective noise. واضح? Okay, so if you have, for example, 16 PSK and 16 QAM, in terms of bandwidth, they are the same, because remember, bandwidth is a 1 plus D times S, all right? And as we said, D tends to be 1, but regardless, 1 plus D times S, right? واضح? So for QAM, it's 1 plus D times S. For PSK, it's 1 plus D times S. However, QAM tends to be even more noise resistant because of the fact that the symbols are arranged, okay, with some distance between each 2 symbols, which reduces the probability of error. Any questions so far? واضح النقطة دي يا شباب؟ So very quick recap so far. So first, in chapter 4, we talked about digital transmission, where we have a digital signal, okay, that gets transferred over the medium as is, okay, as is, right, using some line coding techniques. So this is what we call digital communication, okay. In chapter 5-1, okay, we talked about digital signal being first converted to analog signal before it gets transmitted over the medium, okay. And here the medium has low pass effect. An example of this is all the wired networks that we have studied for Ethernet and so on, right? Here, the medium has bandpass effect, in which case we have to convert the digital signal to analog before transmission. Okay, and here we receive an analog signal and then we convert it back to digital. واضح? That's what we have done in the first part of the chapter. This part بقى talks about the fact that the input signal for this part اللي هو 5-2, this one, okay, we talk about the fact that the input signal is inherently analog signal. Okay, the input signal is by default an analog signal, but then we have to convert it to another analog signal, okay, before we transmit it over the medium. Okay, so it's analog to analog. So the question is, what examples from real life that we have such a scenario that we have input, because we know that in all cases, or in most of the cases, we talk about digital bits, okay, and then we need to transfer the digital bits over the line. So if we use baseband transmission, like all the wired networks, we know how to do that using the line coding techniques and so on. For some examples like wireless, or as we said before, ADSL, we need to have broadband communication, in which case we need to convert the digital signal to analog before transmission, right? And we talked about ASK and PSK and all the keying schemes, all the schemes that have keying at the end, they tend to convert digital signal to analog, right? Here, we're talking about modulation schemes or analog modulation schemes where the input signal is already analog type. What examples do we have here? So all the old systems اللي هم مثلا radio broadcast, TV broadcast, right? They don't actually convert the voice to digital. They transfer the voice as analog. They transfer it over a bandpass medium or bandpass channel, right? So all the AM radio, FM radio, right? All the TV broadcast stations, the old ones, they use input signal as analog signal. They do not convert it to digital, right? So all the old systems for radio and TV, they use that concept. So here, so for analog signals, if the input signal is analog signal, we used to characterize, remember, we used to characterize the digital signal for the input using digital signals using bit rate, baud rate. We can do that, right? So bit rate, baud rate, all of these are valid. For analog signals, can we use bit rate? It's not bits. صح? For analog signals, it's not bits. So we cannot use bit rate to characterize the analog signal. The only thing that we can characterize the analog signal is the bandwidth, right? So for the analog signal, the only thing we can describe this analog signal is the bandwidth. The bandwidth in the baseband. The bandwidth in the baseband. Okay? So, but still the signal itself has amplitude, has frequency, has phase, and so on. It has all these components or fundamental parameters. So therefore, the modulation schemes in this category, they are also categorized or systematically use these three parameters, the amplitude modulation, frequency modulation, and phase modulation. Okay, so here again, we're talking about input signal analog. We convert it to analog again, and we transmit over the medium. So again, the other question is, why do we have to convert the analog to analog? يعني ليه يعني? Okay, so the problem, حد عارف الإجابة يا شباب? Why do we have to convert the analog to analog? Why do we have to to shift the signal in the frequency domain? أحمد شيخان اتفضل. Not only that يا أحمد, not only that. The medium has bandpass effect يعني صح بس the medium has bandpass effect صح بس what happens if we transfer مثلا for radio broadcast, what happens if we transfer all the signals without convert it to analog? What will happen? Ahmed, if we transfer all signals ايه برافو عليك. yes معناها ايه ان انت you are transferring multiple radio stations okay as is without having to convert them to or to carry these signals over a certain carrier frequency. So all of them they will be transmitted in the same frequency, so they will interfere with each other. And that's why in the radio we have this tuner where we have to change from one station to another, because each station has a distinct and unique range of frequency that is assigned to this particular station. Okay, so the transmitter has to first adjust the frequency of this signal to be in this frequency range, so that at the receiver side you can use the fine tuner and listen to this station only and not to the other stations, or not to have any effect of interference. So again, we have these three schemes: amplitude modulation, frequency modulation, and phase modulation. So type. So very quickly بقى, so the amplitude modulation talks about the input signal is already analog. Input signal is already analog. And we call it the modulating signal. So this modulating signal is fed to this multiplier, and we multiply this signal by the carrier frequency. So here, the end result is that we end up with the amplitude of the composite signal here will be proportional to the amplitude of the modulating signal, except that the frequency of the carrier frequency is supposed to be higher around this center frequency. So when we do this, we end up with the same signal, but it's shifted in the frequency domain. The same signal shifted in the frequency domain. That's the whole thing. Okay, so modulating signal multiplied by a carrier frequency, it gives us the modulated signal, which is AM signal. Okay, طيب. So in that case بقى احنا we did nothing but we shifted the signal in the frequency domain صح around the center frequency. ليه بقى الباندويث هنا? Why the bandwidth have become double the bandwidth of the input signal? Why? The only one who was able to really explain this is the Nyquist برضو. فهو Nyquist قال لك ايه؟ Again, and I will explain this. You don't really have to know the details of this. You can just assume that this is given. So for AM, the bandwidth is double. The bandwidth gets double. That's it. But the تفسير ده ايه بقى؟ تفسير ده ان يعني the signal itself has a baseband bandwidth of B, right? What we did not talk about is what we call the shadow signal. The shadow signal is another shadow signal in the negative frequency. هتقول لي هو في حاجه اسمها negative frequency. There is a shadow signal in the negative frequency with the same bandwidth of the baseband bandwidth of the signal. So when the signal gets shifted in the frequency domain, the negative frequency becomes positive. So you have the signal becomes like this, 2B. Okay, so we cannot just neglect this shadow signal when we do the modulation. Why? Because if we neglect this, we tend to have this shadow frequency will interfere with the other stations. Okay, so we cannot neglect it. So when we shift the signal in the frequency domain, we have to take into consideration this shadow signal that has negative frequency components, which have been shifted to positive when we did this modulation. So Nyquist actually explained this phenomena, and based on that, he said that the minimum bandwidth for the AM modulation is double the bandwidth of the modulating signal. Okay, so that's very easy. So this is AM. For AM, simply the result is that the bandwidth of the modulating signal, the modulated signal or the composite signal for AM modulation is double the bandwidth of the input signal. واضح كده؟ And of course, we all know AM radio. AM radio, we have our voice. Our voice itself has a bandwidth which ranges from 0 to 4 kilohertz, right? This is our voice. صح? So, so if we do a radio broadcast using AM, we expect to have the bandwidth for the AM composite signal to be ايه بقى يا شباب؟ How much? If we were to transfer the voice, the bandwidth of the AM composite signal will be how much? For the case of voice, double it, which is 8. صح؟ صح مظبوط تمام. However, when we take a look at the AM, radio, we will see that AM radio, and you can verify that on your radio physically. يعني. AM radio will start from 530 kilohertz all the way to 1.7 megahertz, right? So we'll see the FM radio how it's arranged later. And as you can see, each station will have, in the AM radio, will have a bandwidth of 10 kilohertz. Why بقى 10 kilohertz? مش احنا قلنا ان هي 8؟ ايوه يا محمد. اللي احنا نسميها guard bands. Guard bands يعني guard bands دي why? Because remember again the filtering at the receiver side is not perfect. So the filtering عامله حاجه عامله زي كده يعني. Okay. فلازم تدي ايه some guard band so that you at the receiver side you can receive the station without interfering with the other stations. Okay. Right. So that's why we have 1 kilohertz on the other, on either side of each station, so that we account for the guard band. So that's why the 8 kilohertz becomes 10. Right. The frequency. So for FM again, why do we have FM? يعني why not stick with AM? Well, FM is again more noise resistance. Okay. So that's good. So the noise affects the frequency less than the amplitude, and we all know that. So this is again the motivation behind frequency modulation. So for frequency modulation بقى, remember here the frequency, not the amplitude, the frequency of the composite signal is proportional to the amplitude of the input signal. Okay. So as the amplitude of the signal is high, as the absolute amplitude of the signal goes high, the frequency of the composite signal also gets high. But the composite signal tends to have the same amplitude. Okay, so we're not changing the amplitude here, we're changing the frequency. So and as we said, in order to have a coherent FM, right, where we avoid the discontinuation, as you can see, there is no discontinuation and the signal here is continuous. So we use what we call the voltage controlled oscillator. The voltage controlled oscillator, right? So if, as I said here, we cannot have 2B, we cannot have double the bandwidth, of course. Why? Because the frequency of the composite signal is proportional to the amplitude of the input signal. So as the amplitude of this input signal gets very, very, very high, the frequency gets very, very, very high. And when the amplitude gets low, the frequency gets low. هتقول لي طب يعني what about signal بقى infinity? We cannot have infinity, of course. At the sender side, we have to clip the signal, we have to control that. And that's why all of this is summarized in this factor here, which is, it's supposed to be beta, not B يعني. So this beta actually is the amount of frequency components that you can accommodate in FM. So usually this value is between, again, these ranges are rough, you don't have to memorize خالص. And I will give you beta, يعني in all cases I will give you beta. So the beta here is from 4 to 20. It's that high, okay? So again, this beta actually depends on the amount of frequency ranges that you can accommodate, because as the amplitude of the input signal gets very high, the frequency of the signal gets very high. So you have to have a limit. So beta is from 4 to 20. So in that case, the amplitude, sorry, the bandwidth for FM is 2 times 1 plus beta times B. طيب. So for FM بقى, we'll see that FM طبعا يعني كلنا on the radio, if you notice, FM starts from 88 megahertz all the way to 108 megahertz, right? But here بقى, the bandwidth is 200 kilohertz. The bandwidth is 200 kilohertz. What is the value of beta here يا شباب؟ حد عارف؟ حد يقدر يجس؟ أو يعني يعرف بالظبط؟ قبل كده كانت 10 kilohertz, right? Now it's 20 times. So see, the FM has 20 times the bandwidth of AM, right? So what is the value of beta here? The value of beta here is 19. Okay, why? Because it's the bandwidth for FM equals to 2 times 1 plus beta times B. So 2B is, as we said before, 2B is kind of 10 kilohertz, right? So this is 1 plus beta becomes 20, which means that beta is 19, is around 19. So use 19 beta to present the. So the last one بقى, for phase modulation, this is the last slide, يعني. So for phase modulation, here we do the same thing, but if you look at the signal here, the phase of the composite signal, the phase, not the frequency, the phase of the composite signal, okay, is proportional to the amplitude of the input signal. Okay, طيب. So in that case, again, the idea behind phase modulation is to try to be noise resistant, but at the same time bandwidth efficient. Noise resistant, but bandwidth efficient. So there is a theorem, يعني, we don't have to go through it, that PM is exactly equivalent to FM after taking the derivative of the input signal. Okay, this is the derivative. Okay, so instead of changing the phase based on the amplitude of the input signal, we will change the frequency of this signal based on the derivative of the input signal. Okay, so this is exactly equivalent to FM. However, before we feed the signal to the voltage controlled oscillator, we need to take the derivative of the input signal. That's the only thing. Okay, and as you can see, if you work on the derivative of the signal is always less than the absolute value of the signal. Therefore, the range of frequency is much less. And that's why the value of beta here, is from 1 to 3 actually. Which means that in terms of bandwidth efficiency, the phase modulation is much more efficient compared to frequency modulation. Phase modulation is much more efficient. So if we were to summarize all the AM, FM, and PM. So AM, so the bandwidth, the bandwidth for all cases is actually 2 times 1 plus beta times B. So for AM, what's the value of beta, shabab? 0 بالظبط. For FM, the value of beta is from 4 to all the way to 20. And for PM, the value of beta is from 1 to 3. Okay? So you can consider this is a general case. Of course, beta is already known for the case of AM, 0. But for FM and P, of course, you don't have to memorize all these ranges. I'm going to give you beta, except for AM, of course. So you don't have to memorize all these values.